Hello everyone, Victor is here, and in this video I want to talk about the pKa table and how to properly use pKa table to solve your acid-base related questions. First of all, there are many different types of pKa tables, and you are probably going to see one in your course materials, your instructor might give you one, or you are definitely going to find one in your textbook. I'm purposefully not showing a pKa table here simply because, I don't want a copyright strike from one of the publishers out there. That's why I'm showing my own pKa table over here, which you can get from my website. Also, as I said, you can get your pKa table from your textbook or your instructor. Sometimes instructors like a specific style of a pKa table, so they will provide you one that you are going to be using on the exams and maybe during the homework and other class activities as well. Your pKa table may be organized the way I like to organize my pKa table based on the functional groups. However, there is another style that is quite popular as well, which organizes the pKa values rather than functional groups, and it goes from lowest to highest or highest to lowest. And while in my opinion the organization by functional groups is a little bit easier to follow, the organization by the pKa values also has its own benefits when you are solving certain type of acid-base problems. But one thing that you're probably noticing about this pKa table right away is that while it may contain a lot of different compounds, it obviously does not have every single compound you're ever going to see in your course, and it's definitely not going to have every single compound you're going to see on the exam either. So how are we going to deal with that? And in this video I am specifically going to go over the details how you can estimate the pKa values for different compounds based on the values that you have in your pKa table. Let me illustrate that with a couple of examples. So here is a molecule, and let's say you need to use this molecule in an acid-base reaction and you need to know the pKa of this molecule. If you're going to look at my pKa table or the one in your textbook, you're going to be hard-pressed to find this exact molecule, which means that, well, while we cannot find the exact value for this compound, and you probably don't know how this compound is called, so you cannot just Google that, we'll have to use the best approximation based on what we have in our pKa table. In order to do that, the first step is to recognize the type of a functional group that we have in this molecule and go from there. So what I have in this case is a nitrogen connected to an sp3 hybridized atom, and nitrogen itself is sp3 hybridized as well. So I have nitrogen, I have sp3 hybridization, so all of that pushes me towards the fact that that is some sort of an amine group. On top of that, I see that this nitrogen is positively charged, which means that that is going to be a protonated amine. So protonated species, which means that in my pKa table I would look it up next to other species where nitrogen is positively charged. So this one is probably going to be the closest to something like CH3NH3 in my pKa table. And if I look up the value for that one, I'm going to see the value of 10.6. Now, the experimental value for the pKa of this molecule is going to be 983. So overall, you can see that our value that we got from the next closest compound on the pKa table is not quite the same. It is close enough, so for the most purposes, for most examples that you are going to be dealing with in the scope of organic chemistry, it will be close enough. So for the next example, I have an alcohol that looks like this. Now, again, if I wanted to figure out all the features of this molecule to look up something very similar in the pKa table, I see that I have the oxygen atom over here that is also sp3 hybridized oxygen, and it is connected to the sp3 hybridized carbon as well. So overall, that means that that is an alcohol. Now, the alcohols, they have pKa values somewhere around 16 to about 18, and primary alcohols are roughly 16, secondary alcohols are about 17, and tertiary alcohols are about 18. So this is a primary alcohol, so I would expect the pKa value for that one to be somewhere around 16. So if I needed to estimate that value, I would say it's about 16. Now, if I look at the experimental value for this guy is going to be roughly 15. So again, while we didn't hit the nail on the head, we are close enough. Now, how about something like that? What type of a functional group is that? Let me know in the comments below if you can identify this functional group right away. This, as a functional group, is the carboxylic acid. And I know that the pKa of the carboxylic acid from my pKa table is typically somewhere between 4 and 5, give or take, depending on the exact nature of this carboxylic acid. So let's say I'm going to estimate it at around 4.8, because that's where most typical carboxylic acids are. They're around 4.8, 4.6 or so. Experimental value for this molecule is going to be 4.86. So in this case, we were actually extremely close. And if I needed to do any kind of calculations using this number, my calculations would actually be very close to what this molecule represents in reality. Alright, how about this guy? This is a protonated quinoline. And the molecule might look big and scary and intimidating. However, don't get intimidated whenever you see a big molecule like that. Start breaking it down based on what you see in this molecule. So here I have a nitrogen, and that nitrogen is going to be sp2 hybridized. So that is sp2 hybridized nitrogen. Also, I'm seeing that I have a positive charge, so that is a protonated species. And another important thing that I'm seeing here, that I have this feature around my nitrogen where I have a 6-membered ring with the alternating single and double bonds, so that part looks to me like an aromatic compound. So I will show that this is an aromatic species as well. So in my pKa table, I'm going to look for a 6-membered ring with the nitrogen inside of the ring with a positive charge, and the ring should be aromatic. The closest match that I can find in my pKa table is going to be this molecule like that. This is a protonated pyridine, and it has all the same features that my quinoline, that my original molecule. It is also aromatic, it is also protonated, the nitrogen is also sp2 hybridized. So based on all the considerations here, the pKa for those molecules should be fairly close. The pKa for the protonated pyridine is 5.2, and the experimental value for protonated quinoline is 4.9. So quite close. I would say that the difference of 0.3 in the logarithmic scale is actually not that bad at all. Well, how about this molecule? On a surface, these two molecules might look very similar. However, there is one exceptionally important difference, and the difference is that my nitrogen now is not the part of the ring, but it is attached to the ring, which means that whenever I'm looking for something similar in my pKa table, I would have to look for an aromatic ring, and now my nitrogen is not on the ring but attached to it like that. So I should be looking for something of this sort. And if I look at my pKa table very carefully, I will find this exact species, which is going to be at 4.6 pKa wise. By the way, sometimes in your pKa table you might have the aromatic ring, this part abbreviated as pH. So the molecule that I have drawn here in blue could have been shown as pHNH3+. So remember that pH means the aromatic ring, and sometimes it is hiding, so it might not be necessarily apparent right away, but keep that in mind. Now, coming back to my molecule, the experimental value that I have for the protonated amine of phthalate that I have as the original molecule is actually around 3.9, so not as close as in the previous case, But again, as I said, for our purposes, that will be close enough. And if you were to use that value on the exam, then your instructor would full-heartedly expect you to use the number 4.6, because 3.9, the experimental value that I have over here, unless it is given to you explicitly, you will have no way of knowing, because I can guarantee that a regular pKa table that you will have in your class will not contain that compound. Now, how about this little guy over here? Again, if you recognize your functional groups, you will immediately recognize that we have a carboxylic acid here again, and we have already seen carboxylic acid before, and we said that the regular carboxylic acid was somewhere between 4 and 5, a little bit closer to 5. So in this case, I am tempted to say that this molecule's pKa is again somewhere around 4.5 or so. However, there is a very important distinction here, and the distinction is that I have those fluorine atoms connected to my molecule extremely close to the functional group itself. When we have extremely electronegative elements like fluorine, and fluorine is the most electronegative element that we have on periodic table, when we have something like that sitting next or very close to our acidic hydrogen, that increases the acidity significantly. So we might not have this exact molecule in our pKa table, but we will know that because of those three fluorines, our pKa should be way less than 4 or 5, so probably like maybe even 1 or 2 or something like that. The next closest molecule that I could find in a typical pKa table was trichloroacidic acid, which looks like that. So this guy is estimated to have a pKa of about 0.64, and since fluorine is more electronegative than chlorine, we would estimate that the actual pKa for our trifluoroacidic acid is actually less than that. And based on the information that I could find on the internet, the pKa of the trifluoroacidic acid is somewhere around 0.2. Well, let's look at a couple more examples. In this molecule, I am immediately noticing that I have a sulfur with a hydrogen, so I should be looking for something containing sulfur in my pKa table. And there are a couple of different things that I see in the pKa table with the sulfur, so that should be a direct sulfur to hydrogen bond. Another important thing to notice here that this sulfur atom that I have over here is right next to the sp3 hybridized atom, and it is sp3 hybridized on its own, which means that the presence of this aromatic ring over here is essentially irrelevant. It's not directly on the aromatic ring, it's not going to be influencing it much. The closest value that I could find in the pKa table was the ethyl thiol that looks like that. The pKa of that molecule is estimated to be around 10.5 or so, and the experimental value for the molecule that I have over here on the screen, so this one is actually around 9.5. So 1 point difference, I would say we're close enough for our purposes. And the final molecule is going to be the trickiest one. Looking at this molecule very carefully, I am not seeing any hydrogens sitting on oxygens, on nitrogens, or sulfurs. I am not seeing any positive charges or anything of that sort. So where is my acidic hydrogen here? And there are actually quite a few different places where we can find that hydrogen, so questions like that might take you a little while to find that acidic hydrogen. In this particular case, the most acidic hydrogen is going to be hiding over here between two carbonyls. The functional group on the left is going to be a ketone, the functional group on the right side is going to be an ester, and when those two are sandwiched next to each other like that, the carbon in between is fairly acidic. So the chemistry of those elements and a lot of acid base of those guys will be typically covered in the second semester of organic chemistry, so hopefully you're looking forward to that. Now, in my pKa table, the closest thing that I can find that resembles something of that sort is going to be acetylacetone over here, which has specifically those two hydrogens in the middle of the molecule between the two carbonyls as well. In this case, if I were to look up the pKa value for that, that's going to be roughly 9.2. The experimental value for my actual molecule that I have here is about 10.9. So again, we're fairly close. Once you talk more about the acid-base properties of carbonyls and species that we refer to as enols and enolates, you will learn to distinguish between the ones that have pKa roughly 9, pKa roughly 10, 11, and 13, and then you probably won't even need your pKa table anymore to see those. So in a nutshell, this is how you're going to be approaching your pKa table. Do not look for exact molecule in the pKa table. You might get lucky and you might get the exact molecule that you are dealing with right on your pKa table, but in most cases chances are you're not going to have one. So in this case, focus on the functional group that you have on your molecule, see what kind of features the molecule have, and look for the same features in the pKa table. Does the molecule have a plus charge? Does the molecule have heteroatoms? Do we have any functional groups that we recognize? Focus on all of those features, and then it will be much easier to find the next closest thing in the pKa table and take that number. Remember that nobody expects you to know the exact number, exact pKa value for a certain molecule unless this number is of course given to you. So on the exam and in the homework, we are going to be using the next best value for us. And another thing to keep in mind is that many instructors are very particular about a specific pKa table that they like to use. So if your instructor provides you with a specific pKa table that they like to use, make sure that you become very familiar with that pKa table, because you will see that numbers can change slightly from one table to another one, because different pKa tables have different points of reference from where they took those numbers. So don't be scared that number for the seemingly same molecule can vary a little bit from table to table. That's quite natural based on how exactly those numbers were measured. Well, hopefully this video clears up how to use the pKa table. Let me know what kind of questions you have in the comments below, and I'll see you in the next one.